Well, we're going to take a short break from thinking about our reactions and talking a little bit about a thing called tautomerization. Tautomerization is kind of like resonance, but not really, because it's actually a reaction. We actually move some hydrogens. Um, Now, we're going to be talking about hydration of alkynes. And if you do a single addition of an OH to a alkyne, you would form an alkene that has an alcohol off of it. And this is known as an enol. This enol has the ene from the double bond and then the ol from the alcohol. That would be like what you kind of assume is forms, but the issue is that's not actually what is isolated. These can undergo this tautomerization or this rearrangement to form something that's going to be more stable. And it's going to form what we call a keto, which is going to be, or it's going to form a ketone or an aldehyde. But this tautomerization is we call KetoEnol tautomerization. So we're going to kind of focus a little bit about this kind of tautomerization first before we think about any like hydration reactions. But the kind of general thing that we want to take away from here is if you form an enol, meaning an alcohol directly attached to a double bond, this can rearrange to a different type of structure. And this keto-enol tautomers are going to kind of have this abbreviation, keto coming from the word ketone, and then enol coming from your alkene and alcohol. Now, there are a bunch of different ways in which you can form this kind of tautomerization. But the first thing before we even get there is what types of structures have the ability to in the first place. So let's go ahead and look at just a variety of, if I can scroll, a variety of structures and see which of these are enolizable. Word doesn't think that's a word, but it is. So here are a bunch of different examples of ketones or aldehydes. And our first thing is going to be thinking, do they have the ability to form an enol? And in order for that to happen, there needs to be a hydrogen, which is attached. We'll call this alpha. We'll focus more on this kind of like nomenclature of alpha, beta, and stuff in Unit 4, but kind of one away from our functional group. So if I look at this very first example, this benzophenone-like structure, or benzophenone, if I look here at the spot one away, so I have my ketone one away to my left or right, if there is a hydrogen there, that means it is enolizable. And you can get a double bond between that ketone and that hydrogen. So this can tautomerize, which we show with this equilibrium arrow, not resonance arrows, but actual equilibrium. And this would give us the ability to rearrange or tautomerize into this enol. Now this enol is going to be your less favored. You're going to prefer going to your ketone, but this is the kind of conversion between those. If we look at the next structure, which is going to be the one that has benzenes on both sides, both of those benzene spots, kind of like right here and right here, neither of those have any hydrogens, so this is not enolizable. So this is not a structure that can form an enol, mostly because you'd end up getting a Texas carbon. So if I imagined putting and then here I'll just do BZ or phenyl. If I try to put a double bond here, my paper lights on fire because this right here is an expanded octet. So you need to be able to have a hydrogen there to actually kind of get that kind of like elimination product. So this one we're going to erase because I don't want anybody to ever see I drew that again. Is not able to form a tautomer. It's not enolizable, cannot turn into an enol. For the same reason, if I look at my formaldehyde here, this is also not enolizable. There is a hydrogen, but it's not one away, it's directly attached to our ketone. Over on our last example here, there are actually two hydrogens here, which are perfectly able to enolize, and then we could form our enol. We'll do it here, H, OH, and then you can do it on the other side as well. So in terms of identifying, are you able to interconvert between a ketone and an enol? Enols are nice and easy. If you see a double bond that has an OH, that's definitely enolizable. It can go to a ketone or an aldehyde. If you have a ketone or an aldehyde, your main thing that you're looking for is, do you have a hydrogen that's going to be one-off that's able to form? Now, there are a ton of different reaction conditions we can use. We can use acid or base. Both of them are able to give us our structure. So let's briefly look at the mechanism to convert between a ketone and an enol for kind of like every different possible condition. And then I guess there's 4: ketone to enol in base, ketone to enol in acid, enol to ketone in base, and then in acid. So we'll look at kind of all of these. We'll start with our acidic, then we'll go with our basic. So each of these are going to kind of have some acid-base chemistry and then the kind of rearrangement to get that specific ketone or enol. So often kind of like a elimination like move. So our first one is going to start with a ketone, and then we're going to go to an enol. So let's go ahead and start with our generic ketone. And then this is going to be under acidic conditions. So we'll use our acid-base arrows. If I think of a ketone, and I'm trying to identify what is going to be the most basic atom, it's going to be our oxygen because that has lone pairs. This can come, actually, I'm going to draw this actually. I'll give you your spectator. I'll just do HX. So you can imagine this like being HBr or something. This can come and become protonated and then kick out our leaving group, giving us our the conjugate base there. So this would give us our protonated with now a plus charge for our ketone, and then you'll then also generate your conjugate. Here we'll just show X minus. Now, in this case, while you're able to just do the reverse reaction, so that X comes, pulls off that H, giving you your 2 lone pairs back in the oxygen, there is also your other H, which is that enolizable one that we were thinking about just a second ago, which can also be abstracted. And in this case, if we come and get this to abstract, we can make a double bond here and then give the lone pairs of the oxygen again, slightly different way, but the same kind of general form. This is also has some equilibrium, and then this is going to give us our enol, and then it will actually generate more HX, which is what we started with. So this is why this is catalytic. So take a ketone, add acid, we can get an acid base step to protonate our ketone, and then we can get this like elimination-like thing where we abstract a proton, make a double bond. Instead of fully kicking out our leaving group, we go from a double down just to a single bond, and that's going to form our enol. And that's our kind of first type of mechanism to convert between the two. And we're going to do this exact same thing under all of our different conditions. There's slight nuance, but the kind of general same theme will happen again and again. So now let's do the opposite. Let's go ahead and start with our enol and go to our ketone. Just kind of show like the reverse reaction, because we see that we have these equilibrium arrows throughout. So there is our starting material, and then we're going to react this with our acid. We'll just show our HX. Here we're going to get back to our middle spot. So we're going to want to form our double bond, and then our double bond, it does its attacking stuff, electrophilic addition, and then kick out our bromine or whatever our halogen is. Generally, these last 2 arrows are the same as our normal electrophilic addition. This is just kind of kick-started by the lone pairs of the oxygen coming in. That is going to give us our protonated version of our ketone. And then we then get our X minus. And then that X minus will come do what we were talking about on that first reaction, where it just simply pulls off your it pulls off your hydrogen rather than does your enol stuff, giving you your neutral ketone and then more HX back. So this is just literally the reverse reaction, but I wanted to kind of show that separately with kind of the full sets of reaction arrows. So formation of your kind of same reactive intermediate, which is that protonated version of your ketone, and then the choices whether or not you abstract a proton attached to the oxygen or the proton in the enolizable condition, which is your alpha or your one away. So those are your kind of acidic conversions between your ketone and your enol. You can also do this exact same type of stuff under basic conditions. So let's go ahead and work through that conversion, starting with our ketone. So we'll go ahead and start with our ketone. And here for our base, we'll do our hydroxide. Now, if I have hydroxide, my hydroxide is going to be on a base. It's going to be a stronger base than our ketone would be, mostly because it's charged. So if I think about my structure here, my most acidic proton is going to be the one that's going to be in that enolizable spot or one away from my ketone. So we can come abstract that, make your double bond, and then here, this is just going to resonate up to give you your O-. This is actually the same type of stuff that is you could actually have shown in the Mechanism Monday during our second Mechanism Monday. This is going to give us our kind of like deprotonated version of our enol, because this is going to give us our O-, and then it's going to generate water. Now, this oxygen can do acid-base stuff. It can grab a proton from water, giving us our ultimate enol, and then generating more hydroxide base at the end. So here, we're again starting with acid-base stuff, but here we're going to use our base rather than our acid. So that's going to form our deprotonated version of our enol, which can then become our enol via water, or whatever our conjugate acid would be from our initial base. We can also do the reverse reaction, going from our enol to our ketone under basic conditions. I guess this is on the next page. So if we start with our enol, and we subject this to basic conditions, here, if I'm thinking of our most acidic proton, it's going to be on our alcohol. Generally, H's that are going to be attached to non-carbon stuff will be more acidic than attached to carbon stuff. So this can come, abstract our proton, and give us our key intermediate. That key intermediate is going to be that enol that's deprotonated, and then this will generate water. And then, much like we saw earlier, this can come down, forcing our electrophilic addition, and then generate more of our base. That gives us our ketone, and then gives us more base. And this is just kind of our max attempt to show all the possibilities to show the conversion between our ketone and our enol, or our enol and a ketone under acidic or basic conditions. They're all going to be through our kind of core reactive intermediate, which will either be our ketone that's protonated or our enol that's deprotonated. We walk through these as kind of like 4 separate mechanisms, but it's kind of the same thing, just kind of again and again and again. And this is just the kind of conversion between our ketone and our enol. One of the main things is our ketone is going to be more stable. So when we're thinking about our reactions, we're going to favor our formation of our ketone rather than our enol. Now, much like our addition to our alkenes, when we form our hydration reactions, there are going to be 2 main ones that we're going to talk about, which are going to be super, super similar. Remember that we could use just simple acid, but the issue with that is you can get some rearrangement because you form a carbocation. The other 2 was using your mercury stuff or your hydroboration. Exact same stuff here. We can use our mercury stuff or we can use our boron stuff. Our mercury stuff, here we're going to use just a slight difference. That's almost the same, just a little bit difference. Here we're going to use our mercury ion. So our mercury sulfate is going to be our most common one. And then typically this is done with water and sulfuric acid. So this will be under acidic conditions. If you use this, this will add a OH in your Markovnikov spot. So in this case, on our terminal alkyne, we prefer it over on the inside. So this is add OH on Markovnikov side. And this will make our enol. Now that enol is going to be our core kind of like intermediate, which will then tautomerize to our ketone. And kind of like without drawing it fully, like the full mechanism and everything, in general, just kind of imagine like this double bond kind of like hopping down and making it to your, this is not your mechanism arrow. Please don't draw that as a mechanism. You'll draw the full mechanism like we showed above. But imagine that double bond just kind of hopping down there to give you your ketone. So tautomerize to your ketone. And this will be your major product from your hydration of your alkyne. And this feels a little bit weird because we say hydration and you're like, I think I should make an alcohol. Well, you do make an alcohol, but it rearranges to a ketone. And it also does feel like, hey, I go from a triple bond down to like nothing, but you do actually go down to a double bond, but the double bond to the oxygen rather than to a carbon. Now, if you want to form the anti-Markovnikov, much like how we would use our sodium borohydride, often we use like something like BH3 with THF. Here we often will do it a slightly different version, but still a boron. So I still have my boron stuff here. One of the most common is Sia, not the person who swings from a chandelier. I hope that's the right song reference. SIA. SIA is a carbon group that has a more complex name that you can use to stabilize that boron. And if you use this Siamyl, or Sia for short, boron species with peroxide, and again, that peroxide is going to be our hint that we're going to go anti-Markovnikov, and then base, so our most common will be our sodium hydroxide. This will be your adding your OH on your anti-mark. This also forms a, I don't know how the heck I drew a star there, but I drew a star, to make our enol. That enol will then tautomerize to our ketone. In this case, it's terminal, so it goes down to an aldehyde. And that's going to give us kind of that ketone in the or aldehyde, I guess I should say, on the anti-Markovnikov, or on the side where there's less H's. So those are our kind of like two major types of reactions. Small, super similar to what we see in our alkene chemistry. Mercury stuff to go Markovnikov, boron stuff to go anti-Markovnikov. The only slight kind of wrench we put in this is if that rearranges through this tautomerization to form ketones and aldehydes rather than having these enols, because we can get more stable structures. So that's the one that you'll kind of like, when I do problems like this, I will actually draw out the enol and then I'll draw out the ketone. I will very rarely go from the triple bond directly to the ketone or the aldehyde without drawing that enol. And each of these can be formed by the kind of values that we see above under kind of our acidic or basic conditions. So we'll go and stop there. And then in our next video, we'll actually walk through our very final set of electrophilic addition reactions to our alkynes.